We introduce UniDexGrasp++, improving dexterous grasping policy learning via geometry-aware curriculum and iterative generalist specialist learning. Dexterous hand grasping is a vital problem for both the vision and robotics communities. However, it's extremely challenging and underexplored to handle universal, large-scale dexterous hand objects grasping of various categories, especially from realistic visual signals as input. We find that directly learning a vision-based policy will result in low performance and generalizability. Thus, we introduce our method, UniDexGrasp++, which tries to train a good enough state-based policy and then distill it to a vision-based policy. Additionally, we enable the policy to handle diverse tasks through partitioning the task space and then specialized tuning on each subspace. In our method, we first train a state-based policy. Then, after specialized fine-tuning, this policy has a better performance. After that, we distill it to a vision-based policy. We then fine-tune the vision-based policy to the final good enough policy. For state-based policy learning, we introduce a geometry-aware task curriculum learning strategy to help the policy learn and grow up step by step. We use geometry-aware features extracted from Point Cloud Autoencoder to carefully design each level of the curriculum for the state-based policy. After we get the trained state-based policy, we further fine-tune it to a better one. We first use the geometry feature to divide the contiguous task space into several clusters and assign each cluster to a specialist to learn some specific knowledge. Here, for the task space clustering, we introduce our geometry-aware clustering technique. Each specialist will be assigned a subspace of the task space to learn specific knowledge. We then train each specialist under the assigned task cluster and then distill it to the generalist. We follow this step several times until the policy is good enough. After we get a good enough teacher policy, we distill it to a vision-based generalist. Then the vision-based policy is further fine-tuned utilizing similar geometry-aware iterative generalist specialist learning until it becomes a good enough vision-based generalist. For vision-based policy, we utilize the visual features from the learned vision backbone, which help the clustering more task-aware, which is also what we want. Then the policy will benefit from each step of our training and have good performance and generalizability to handle the challenging universal dexterous grasping problem. We now show the performance of our training process. After geometry-aware task curriculum, our state-based policy can obtain a relatively good performance. Then the geometry-aware iterative generalist specialist learning further increases the success rate significantly. Although the performance drops after the state vision distillation, our vision-based fine-tuning works well and finally get a good vision-based generalist with an 85.4 success rate. We compare our method with the previous method and evaluate them on the training set, the test set consisting of unseen objects, and the test set of objects from unseen categories. The result shows that our method improves the performance significantly under the state-based setting. For vision-based policy, our method also outperforms the previous SOTA methods by a large margin. Here we show some demonstrations of our methods. Here is our diverse training set, which contains more than 3,000 object instances and their diverse initial poses. We train the policy in a high parallel simulator, Isaac Gym. Here we show some results of our geometry-aware clustering and corresponding grasping results. Thanks to the learned features from the vision backbone, our method can cluster the task space based on the object geometry, pose, and the corresponding grasping strategy of the policy. And we thus have similar grasping strategies in the same cluster. And here we show some grasping processes of different objects with different poses. Thanks for watching.